if you were a mouse developer, wouldn't it make a lot more sense to have a proprietary mouse and keep all that mouse stuff secret? No, absolutely not. You want to have a mouse that plugs and plays with everyone else's infrastructure. No one wants to go back to that. Let's configure everything by hand.
Hey guys, welcome to Embedded Toolbox, a video interview series where we try to save the world by solving one engineering challenge at a time. And this week we are solving the problem of scaling smart sensors into the entirety of the industrial IoT. And to help us do that, we have Doug Sandy, who's the CTO of PICMG. How you doing, Doug?
I'm doing great. Good to see you, Brandon.
You too. So I think it goes without saying why we need to be able to scale smart sensors. There are supposed to be billions of these things all over the world, but I think we should start at why is there a challenge scaling them in the first place? I think that's probably the best place to start.
Yeah, sure. So let me tell a very short story here. Suppose we are trying to create a smart factory. So a factory with equipment that is customized and has lots of smart sensors and smart effectors, smart actuators, smart motors that can control things. This is a little different than the normal IoT configuration that you probably see in the media. In industrial IoT, in smart factory, you need to control things. So in this highly customized factory, you want to bring on a new piece of equipment, and you go out and buy a sensor. Right now, the state of the art for a sensor is just 3 analog wires or maybe 2 analog wires. It's not smart in any way, shape, or form. Your challenge now, if you're a factory operator, is to try to somehow create a smart sensor out of that so that it plugs into the rest of your smart infrastructure. Prior to PICMG's specifications, there really wasn't a common specified uniform way of doing this.
Great. So I guess that begs the question, what makes a sensor smart? Why is a PICMG enabled smart sensor any better than those 3-wire analog sensors we have on the market today?
Yeah, sure. So the very shortest way that I can tell you what makes it smart is the sensor needs to report its capabilities to the rest of the infrastructure. So think about plug and play. Here I have a mouse, right? Back in the early days of plug and play, actually before plug and play, if you plugged in a piece of equipment into your laptop, if you had a laptop, or your desktop, I'll say a desktop, you would need to go through this laborious process of downloading drivers and configuring it, maybe going into the firmware of your desktop and making sure everything played nicely together. And then if you did everything correctly, your new mouse would actually work on your system. Now with plug and play, what happens when you plug in a mouse into your system or plug in any plug and play device into your system is the device has inside of it a data representation. We don't call it that way typically when we talk about traditional plug and play devices, but there's a little piece of data that gets transmitted back to the system that they're plugged into that says, hey, I'm a mouse, or I'm a keyboard, or I'm a device X, whatever it is. That's what makes plug and play, and that's really at the heart of what can make a smart sensor smart. Okay. The other part that's required to make a smart sensor smart is once it can identify itself to the rest of the system, there needs to be some means of actually gathering that data in a generic fashion, right? So you don't want to have to go out to say a thermocouple and read a thermocouple, which returns a temperature reading. You don't want to have to go out and read a thermistor a different way. They both record temperatures. You'd like to have an abstracted view of that sensor when you're playing with the rest of the infrastructure. So down at the sensor level, there's device specifics, and then up above that in the infrastructure level, it's a genericized device, much like we have human input devices for laptops these days.
So all of that makes total sense if you're a smart sensor user. But why would you want to do this if you're a smart sensor manufacturer? Don't you want to keep some of this stuff proprietary so that you lock people in, or just because it's the way you've always been doing it?
Oh, well, let me answer that question with a question. If you were a mouse developer, wouldn't it make a lot more sense to have a proprietary mouse and keep all that mouse stuff secret? No, absolutely not. You want to have a mouse that plugs and plays with everyone else's infrastructure. No one wants to go back to that. Let's configure everything by hand so that we can use this proprietary mouse.
What's PICMG working on to get us there?
The secret ingredient that makes this all work together is that data representation. How does a smart sensor, when it's plugged into the rest of your infrastructure, report itself so that the rest of your infrastructure knows that it's a thermistor or a thermocouple? Actually, it's a temperature sensor. We're abstracting out the exact device specifics. Or maybe it's not a temperature sensor. Maybe it's a pressure transducer or something else, right? So how does it know? So PICMG came up with another specification that's iot.1, which is our firmware and data model specification, which defines the data model, what has to be represented in order to have this generic plug and play endpoint. So when you plug it in, it messages the rest of your system in a standardized way and provides the data model for your system so it knows what it is and how it can control it or how it can read it.
Great. Can we take a look?
So this is the PICMG GitHub repository. We normally in the past have released open standards and open specifications for embedded computing. With this specification, iot.1, we have also released a whole bunch of open source code that is representative of how to use the specification. So here we have an open source firmware that can be used for the ATmega 328 processor. We have a builder, which builds, it's an intermediate step. I'll show you a diagram for that. And we have a configurator. So let me just open up the configurator. All of this is available online. You can download it if you'd like. Now, the way these tools work together is you as a sensor vendor or a sensor integrator, you've got your intelligence module, whether it's microsam or something else, you've got your sensor and you want to create a smart sensor. Well, the steps that need to happen are, well, you need to get those sensor specifics and you need to kind of create source code and then build that source code in order to create the firmware for the endpoint. Unfortunately, you probably don't want to write the source code, right? No one wants to do that. There needs to be like an easy button for this. So imagine
does anybody write?
Easy button.
Does anybody write that anymore?
I will tell you, I spent a lot of this past year writing source code for firmware, so that the users of these specifications don't have to, right? So we have representative code out there. The concept, though, when we came up with this iot.1 specification is that you could somehow configure the device without having to write a stitch of source code at all. So the specification defines all the data structures required for this thing on the left-hand side of the diagram, the device configurator. So you see multiple libraries, one for the device, the intelligence module that you're using. You see library code for the sensors and effectors that you might use. And also there might be some state sets, and we aren't going to get into that as well, but it's another library. Now, somehow you use this configurator to create an output file called config.json. We don't define in the specification how the configurator works, but never fear, we have an example on GitHub, and I'll show you that. Once that config.json file, that data model gets spat out of the configurator, then there's some backend tools that can use that to build the rest of the firmware. And rather than just say, hey, it's magic, somehow it could be done, PICMG has actually created a builder, which is that intermediary. It takes the configuration file and creates a C file and a header file with all of the specifics for your configuration to drive the rest of the build process. And then we did create a piece of example firmware that can take your configuration using the GNU toolchain and create firmware for your device. So there it is in a nutshell. And probably wondering, okay, how real is this, right?
Right. I was gonna say, so if you had all of the everything that you needed, you know, all of your foundational building blocks in order to build the smart sensor, and you've downloaded all of the tools and you have the source code and you're ready to go from PICMG, how long would this take us, Doug? How long would it take us to get a smart sensor communicating, you know, abstracted data?
Do we have like 3 minutes on your show here?
We do have 3 minutes. We'll extend it out.
Okay, let's I'm going to open up my tool chain here. It's on another computer. Okay, here we are on the tool chain computer. And what you see in front of you is this representative IoT device configurator that we've already installed onto this system, but it's exactly what you could get from that PICMG GitHub repository. And we're going to make a new sensor. So we're going to start out and we're going to go to the sensor library. And here we have a sensor that is a thermistor. And we're going to start with this kind of as a base thermistor. But the thermistor that we're going to create is, let's say it's a PICMG special. So it's a PICMG thermistor, and it has a specific part number. Let's just say it's 1, 2, 3, 4. And we could put in some sort of description if we want for this sensor. So it's an example sensor. It hooks up to an analog channel, and it doesn't have any maximum, special sample rates. It's going to measure in degrees. Let's make it measure in degrees C. Okay. And then all of this stuff typically would be data sheet information.
Right.
And let me just show you, in fact, I had here's Vishay. They make a whole line of different thermistors. And one of the nice things about this site here is you can actually also get a printout of their device curves or a CSV file of their device curves. So let's have them calculate. There we have, here's the device curves for this particular thermistor. We could export it to a CSV file. And this CSV file, there's nothing special about it. It's temperature on one column and then the resistance measured on another column. That device curve representation is what's important for actually creating our sensor model. So what we're going to do is we're going to select a device curve for this. We're going to get a response curve, and let's pick, boy, there's a lot of them in here. So here we go. We'll just pick this one. And let's view it to make sure it came in. And yeah, that looks like a negative temperature coefficient thermistor. So, okay. Now, once all of this is done, we're going to save the changes. Boom. And now we've created a new sensor library entry for PICMG. There it is, the PICMG 1, 2, 3, 4 temperature sensor. And now once we have this library done, so far it's pretty easy, right, Brandon?
Yeah.
Okay.
Super simple.
Super simple. Now we're going to go ahead and create the configuration for our firmware. So first thing, this field replaceable unit record contains information about our device. It gets reported up to the rest of the infrastructure. So let's just call this is the PICMG. I said it was 1, 2, 3, 4, and we'll call it 1, 2, 3, 4 dash smart. And our part, whoops, I need to hit enter. 1, 2, 3, 4 dash smart. And the part number was, let's just make it 1, 2, 3, 4. And serial number We're being very original here on this. The
Yes.
vendor will make PICMG, and last but not least, whoops, some sort of name, some
Get
name.
creative, Doug. Oh,
Okay.
I was hoping.
Okay, go ahead, Brandon. Go ahead.
Doug's special sensor.
Doug's sensors. Oh, you want special? Okay.
Special, please. Yes.
Sensor.
There we go.
Doug's special sensor. Now, this alone, this just reports what it is, but it doesn't actually create the personality on the module, if you will. We need to tell it whether this is a sensor module or if it's an effector module. Does it have a sensor that you're reading, or does it have a motor? So I chose a sensor, and now we have a little bit of data to fill in this sensor thing. We need to bind it to an analog channel on the device. We're just going to pick one. This one here. And now which sensor do we want to use? Now we're just going to go into our library, and there it is, the PICMG 1234 degrees C. And a lot of these other things are just default values. So gearing ratio is 1. It is possible if you had a motor, you could gear the motor. So that's what this is for. The base unit of this is degrees C. And I'm just going to fill in some of these other things here. It's it measures just degrees C. And we also need to select the input curve for the microcontroller. So this microcontroller, the input curve for it, for the analog channel that we chose, matches the name of the channel. So we're just going to go into configurator, response curves, and it was this 6.8 kilo ohm. Okay, and let's make sure we brought it in. Notice that the response curve for the microcontroller, it's a resistor divide, so it's also nonlinear. And all of this nonlinearity is going to be normalized within the device. So when you read your smart sensor, it's already going to be normalized. You don't have to do any special stuff with that. Okay, so let's create our configuration. We're all done. There's no warnings over here. We're going to export. And we'll put it on my desktop just because that's where it's easy to find. We'll call it Doug's special sensor.
Thank you.
And it's a JSON file.
Got it.
Okay. Okay, now there it is, Doug's special sensor. And you want to see how fast it is to build it? We're going to do that right now. I have a device already plugged in, so it's going to build and program it.
Perfect.
Get past the PowerShell security. And now select Doug's special sensor. And it's building right now. So there it is, it's done. So it's that simple. I think what you can see from this, it actually took much more time to program the device than it did to build the firmware for it.
Right.
But all told, it was a couple minutes to do that. So
wow.
You can go off and get your coffee, come back, and it's all done.
That's pretty nifty, Doug. I mean, really, it is that anybody now can build themselves a smart sensor, it looks like. And I mean, that's, even into the marketing department, right? You did mention, we've talked about sensor manufacturers and sensor users. Who is this IoT.0 and IoT.1, this new family of specifications intended for? Is it more the end user or the manufacturer or both?
Great question. So PICMG is all about enabling markets, right? And we wanted to accelerate the uptake of IoT. And the short answer is yes, all of them, right? We want to make sure that if you're an operator, you have your own factory installation and you want to create your own smart sensor, you can go out there and buy a intelligence module like the micro SAM. You can buy your sensor if you want. You can integrate it to your own sensor that way. Or maybe you're a microcontroller vendor and you want to get into the smart sensor game. You could buy a sensor, create a smart sensor. Or maybe the flip side is you're a sensor vendor and you want to get into the smart sensor game. So we're all about enabling and accelerating. And that's why we took this approach of making it very simple to create smart sensors.